Uh, what about this? I guess all student can hear what I'm saying and can see the shared PPT slide. Okay, so we are well in good shape or good status. So let's resume the lecture now. All right. Let me see. Here, my pen. Okay. In the previous in the last hour, we have learned how carriers or electrons and holes are distributed in conduction band and valence band with the knowledge of density of states and probability of occupancy for each energy state. So using density of state and Fermi function, we can obtain how many electrons are available at each energy state, not for all energy levels. Okay, for a certain specified energy state in conduction band, how many electrons are available. So now we get the answer. Okay, now let's move on to the next slide. Okay, here the only thing that I have modified is instead of NOV, I have used the P of V, whole concentration as a function of energy. And here, instead of using Fermi function, I have used the 1 minus f of V, which means probability of finding not electron but holes. Okay, so 1 minus f of V is the probability of finding a hole in valence band. So similarly, we can estimate how many holes can be obtained in in valence band. So depending on the energy level, how many holes are available at each energy level. So if you're interested in maybe ease of 2 energy level, and going back here, then how many holes are available? Okay, so P of E can be obtained by G sub VE times 1 minus F of E. Okay, so here the dotted line, this indicates 1 minus F of E. This solid line indicates function, Fermi function. Okay, okay, that's it. So if here one more information that I would like to share with you is this area. This area indicates a total Hole concentration. So if you do integration work for all energy levels in valence band, you will get the total hole concentration. And as we have learned, this is a undoped silicon material. So in bonding model, a electron who was originally joined to build up the covalent bonding between two neighboring silicon atoms, if this electron has become free, then always this is now free electron, then always hole has been left behind. So electron holes are created in pairs, right? So the number of electrons is equal to the number of holes as intrinsic carrier concentration. That was 10 to the 10 per cubic centimeter for silicon crystal material. So now this area, let me erase the ink. This area was hole concentration. What about this area? That was N. So they should be identical. Why? Because the electrons and holes are created in pairs in pure silicon material. What was the number at room temperature? That is 10 to the 10 per cubic centimeter. Okay? All right. Now, let's do some more detailed work. How to get the total number of electrons from N of E. So as described here, please do integrate N of E over the range for integration, all the energies in the conduction band. Okay? For what? For obtaining the total electron concentration. So the total number of electrons can be obtained by integrating N of E. So here N of E, right? This is N of E over all the energy level from the bottom of the conduction band to the top of the conduction band. But this integration cannot be solved by hand. It is not possible. So we should use Boltzmann approximation to simplify this function f of v. And here, top edge of the conduction band is not well defined. Well, it is physically, we can define the top edge of the conduction band. However, it is, kind of meaningless work for understanding how electron is moving in the MOSFET, BJT, PN diode, and others used in current contemporary integrated circuit chips. So you can use infinity. But why disclaimer? Why plus infinity is good enough to estimate as the top edge of the conduction band? Because the Fermi function f of E at top edge, top energy level of conduction band is almost zero. So, and the f of E when energy is infinity is still zero. So you can use infinity instead of top edge of the conduction band. Okay, then we can solve this quite complicated integration by hand. So the total number of electron n can be obtained and described as n sub c times exponential minus e minus f over kt. And herein, n sub c indicates effective density of state. Okay, and the right hand side you can see the approximated Fermi function. So here, density of state times Fermi function. So this concept has been well expressed with the two terms, effective density of state times exponential stuff. Okay. So try to remember this equation. The total number of electrons is effective density of states of conduction band times exponential minus is minus EF over KT. So please write this equation maybe 20 times repeatedly. You should memorize this equation. So try to do that. And in next slide, let's repeat the work that we have done in previous slide. So herein we would like to look for the total hole concentration by integrating P of E over all the energy levels in the valence band. For what? For obtaining the total hole concentration. So this is matched to the P of E, hole concentration as a function of energy. And over all the energies in valence band means the top side, top edge of the valence band and bottom edge of the valence band. Okay? And at the bottom of the valence band, the probability of finding a hole is almost 1. So rather than using the bottom edge of valence band, we can use minus infinity, because at the energy of minus infinity, still the probability of finding a hole is still 1, almost 1. So we can simply replace the bottom energy level of valence band with minus infinity. Okay. And this 1 minus f of e is quite complicated. So using Boltzmann approximation, we can simplify it. And then you can do integration work, and you're gonna get this simple equation for total hole concentration P. So here N of B indicates effective density of state for valence band and the exponential stuff. Okay, so still this is density of state times certain probability. So this concept has been well expressed for the equation for hole concentration. So please remember this equation. The hole concentration in pure silicon is a valence band, effective density of valence band times exponential minus what? This time EF minus EV over KT. Previously, here it was EC minus EF. How to memorize it? Always imagine the energy band diagram, and in pure silicon material, the EC is always top, EV is always bottom. So EC minus EF or EF minus EV. And you may not confuse yourself. Okay. So always remember this equation. In previous slide, N, small n, total electron concentration is proportional to the energy difference, EC minus EF. So here is energy band diagram, and depending on the position of the Fermi energy level, if this Fermi energy level getting close to the conduction band edge means this EC minus EF becomes smaller, and this whole value becomes higher. So the number of electrons becomes more and more. So a certain silicon sample has a bunch of electrons. However, that silicon sample doesn't have too many holes. What does it mean? The Fermi energy level for the silicon material has placed near to the conduction band edge. Okay, so maybe in undergraduate class you may remember this EC minus EV, and if EF is here, then you can say that this silicon material is n-type silicon material. So you may simply memorize because EF is close to the conduction band, so it is n-type. If EF is becomes closer to the valence band edge, it is p-type silicon material. So do not memorize it anymore. You are a graduate student. You should become professional in the field of device engineering. So now the electron concentration, hole concentration, you can clearly explain to your maybe parents or friends and your sister, brothers, your friends. not majored in electrical engineering, how many electrons, free electrons can be available, can be obtained in pure silicon material? I guess this is a quite good question for your job interview. You are interested in having a job in, for example, SK Hynix. An interviewer has asked you, how many electrons do we have in silicon material? You said you're interested in working for a semiconductor product. Then you should be very interested in all the electrical properties of silicon material. Then the very simple question is, how many electrons do we have in pure silicon material per cubic centimeter, for example? You should answer 10 to the 10, right? 10 billion electrons at room temperature. Even depending on the temperature, the number 10 billion would be modified. That's true, but simply speaking, at room temperature, because the product is working and verified at room temperature a lot by customers such as Google, Amazon, Apple. So those guys will test the DRAM product of Samsung SK Hynix at room temperature. If this DRAM is working perfectly, then they're gonna purchase the DRAM product. And as a professional, not undergraduate student, you should remember how many electrons and holes are created and generated at room temperature in pure silicon. And then afterwards, you can explain how many electrons and holes are available at each energy state in conduction band and in the valence band. To understand it, you should understand the Boltzmann approximation, some integration work, effective density of state, and stuff, and so on. Okay. Okay, now let's move on to the next one, intrinsic carrier concentration. So herein, you may see that N times NP product, okay, N times P. So previously, we have derived each equation for N and P. So on the left-hand side, this whole thing is equivalent to the total electron concentration, and this whole term is matched to the whole concentration. If you do product, let's do that, and C and B, those two terms are kind of constant, so you can have it in front of the exponential term. And here, let me see, minus, those cancel out, so plus EF divided by KT, and here minus EF divided by KT, so those will be canceled out. So the thing left behind is EC, and here EV, okay, and minus sign is common on both sides, so you can take it in common, and EC minus EV over KT. Now, take a look at this term, EC minus EV. What is it? That is equivalent to the bandgap energy. For silicon, the bandgap energy was 1.12 electron volt. Okay, so herein I have used the E sub G. Then take a look at these three different terms. That is kind of constant, constant, constant. Okay, and N times P, N product P is, as we have learned, the number of electrons and the number of holes are identical because electron and holes are created in pairs, right? So for a given 1 cubic centimeter, the number of electrons and holes are 10 to the 10. That was denoted as N sub I. And now plug in the N sub I here and there. Then this one is Ni times Ni. That is equal to Ni squared. So that is written here. And now this two term Ni squared should be matched to the Nc Nv exponential to the minus Eg over Kt. So from this, we can estimate the intrinsic carrier concentration. The title here, intrinsic carrier concentration, N sub I is this. Okay, so N sub I is a square root N sub C times N sub V exponential minus Eg over 2kT. So here the meaning is, depending on the bandgap energy, the intrinsic carrier concentration can be determined. So for example, let's write down the bandgap energy for each few representative silicon semiconductor material. For example, silicon is 1.12 electron volt, germanium is 0.66 electron volt, which is kind of one half of silicon. Okay, gallium arsenide is 1.42 electron volt. So here is question. In class, you have learned that the intrinsic carrier concentration for silicon is 10 billion per cubic centimeter. What about the germanium? You don't need to answer the exact number of the intrinsic carrier concentration for germanium, but question is, the intrinsic carrier concentration for germanium is higher or smaller, lower than the intrinsic carrier concentration for silicon? You may answer this kind of question. Maybe that would be a good question for your midterm exam. Okay. So once you understand this equation, depending on the bandgap energy, the intrinsic carrier concentration, the total number of electron hole pairs, okay, can be determined and well closely associated. Maybe the linear modification of energy bandgap would affect exponentially the number of free electrons and holes. Okay. So even though the bandgap energy of germanium is simply approximately 50% of silicon bandgap energy, but the intrinsic carrier concentration of germanium is 10 to the 13 per cubic centimeter. As we have learned here, the n sub I of silicon is 10 to the 10 per cubic centimeter. See the difference? 1000x, right? 1000 times difference. Even though the bandgap is simply 50%. Okay, so that is exponential dependency. Okay, all right. So that's all for the intrinsic carrier concentration. So n times p is equal to n sub I square, and Ni was rewritten with the effective density of state for conduction band and valence band, as well as the bandgap energy. Okay, so I guess now it's 1:15. I guess let me have a short break time, maybe 5 minutes. And 1:20, I'm going to resume my lecture. So do not leave your place. Just keep staying there and have a short break time and review what we have learned. Okay. And if you have any question, I will still be in my seat. So please turn on your microphone or leave your message in chatting window. Then I'm going to answer the question. So this is kind of office hour. So please use this break time for 5 minutes. 지원이 학생 잘 들려요? 구지환 어디 갔다? 지환이 있을 텐데 사라졌다. 마이크가 잘 들린대요. 마이크가 없구나. 좋습니다. 김태건 TA 잘 들리고 있어요? 아까 전에 핸드폰이었는데 컴퓨터로 바뀌었네. 잘 들려요? 대답이 없습니다. TA는 어디 간 것 같습니다. 지난주에 물어봤던 김권 학생
네.
있을 것 같아. 아, 역시 앞에 붙어 있는 착실한 학생입니다. 뭐 수업 듣는데 불편함이 있거나 이해가 안 되거나
아,
하는 게 있습니까?
아까 그 방 잠깐 나가줬었는데, 그때 좀
그때 따라하고 있어서.
음향 사고가 있으셨던 것 같은데, 예. 그 이후에는 지금 잘 되고, 잘 듣고 있습니다.
네. 사실 지난 목요일 날 학부 수업 집적회로 수업하다가 사고가 있어서 녹화가 제대로 안 됐습니다.
어,
중간중간 내가 자꾸 끊습니다. 뭐
아,
온라인 강의의 특성상 집중하기가 상대적으로 힘드니 자주 쉽니다. 브레이크
아,
타임을 자주 넣으면서 테크니컬한 이슈가 있는지 살피고 있는데
아,
현재는 괜찮은 것 같습니다.
제가 저 문제만 그런지 몰라도 그 오른쪽 하단에 이렇게 무슨 이렇게 그러니까 무슨 블랭크? 박스가 하나
그거는
있는데,
내가 PPT만 녹화하도록 명령어를 내려서 내 노트북에 지금 학생들 리스트 뜨고 학번 보이고 하는 거를 지금
아,
지우려고 하는 과정이었습니다. 근데 아마
아,
지난주에 녹화하는 과정, 이번 주는 좀 다를 텐데 이제는 진짜 PPT 화면만 녹화가 될 거예요.
네, 알겠습니다.
이거는 지난주는 아마 그게 보였을 겁니다.
네,
크게
알겠습니다.
방해되지 않았을 겁니다.
네, 크게 방해는 안 되는데 혹시나 제
왜냐하면 그
컴퓨터만
화면이 방해하는 만큼 내가 판서를 못하기 때문에
네네,
그 방해되는 화면을 놔두고 판서를 했을 가능성은 제로입니다.
네네, 맞습니다.
놔두면 됩니다. 네, 이번엔 최대한 옆으로 밀어서 안 보이도록 노력하고 있습니다.
네, 알겠습니다. 감사합니다.
중간중간 테크니컬 이슈 때문에 방을 닫고 나오면 학생들이 수업을 잘 듣고 있는지 없는지 감시를 할 수 있는 좋은 방법인 것 같습니다.
네, 재접속을 해야 하기 때문에, 네,
재접속을 해야 되는데 집중 안 하고 있으면 재접속을 안 하겠죠.
그렇죠, 네.
So this is a good idea to close the meeting room and then reopen it. Even though it is happened because of the technical issue, but it is another way to how to check how much each student is each student keeps listening to my lecture. So that is a good idea. I guess close it, and then in a minute, please join it again. Then many students would do that. But if not, then I know you're not listening my lecture. It's a good idea. But I don't do this kind of. I don't do that. 아, 뭐 조금 있다가 수업이 정식으로 시작되면 얘기하겠지만 다음 주부터는 이런 리얼타임 스트리밍 강의를 안 할까 하고 생각 중입니다.
오,
예, 여러 가지 테크니컬 이슈들이 자꾸 생기는 것 같아서 물론 이렇게 실시간으로 학생들하고 만나서 얘기하는 게 필요하다고 생각은 하는데 아주 어려운 일들이 많이 생기는 것 같아서 지금 다른 수업과 동일하게 내가 강의 저장을 해주고 듣는 걸로 어차피 김건희 학생 안 물어보잖아. 질문 없잖아요. 그죠? 질문 있어요, 권희 학생?
아니 뭐,
없잖아 봐.
어,
아이 뭐
아직까지는 네, 없습니다.
아직까지는 그럼 나중에 생길 것 같죠? 안 생기거든. 결국은 내가 일방적으로 떠들 거면 굳이 이렇게
근데,
기술적인 어려움을 겪어가면서 우리가 이렇게 해야 하는가?
아,
그냥 내가 저장해놓고 나중에 편한 시간에 듣는 것도 나쁘진 않은 것
음,
같아서.
근데 확실히 온라인 강의랑 이렇게 저장되는 강의랑 듣는데 좀 집중은 좀 다른 건 확실합니다.
그러니까요.
확실한 건
So
그런데,
for international students, you don't need to worry about too much what I'm talking. I'm just chatting with my graduate student in my group, so just chatting. Okay,
네, 하여튼
그렇지.
각각의 장단이 있는 거라.
알겠습니다. 22분이네. Okay, it's 1:22. Let's resume my lecture. Let me see. Okay. Okay. So now I'm gonna spend another 25 minutes. So please keep concentrating when I'm talking. Okay. Then I'm going to give you another short break time. So that this requires to have all of you awaken through online. Okay, so now let's take a look at the N-type material. Herein, we're gonna repeat the work that we have done for undoped silicon material for N-type silicon material this time. Okay, so the conclusion on the right hand side can be drawn here. The number of electrons as a function of energy for N-type silicon material, not pure silicon material this time. So previously I mentioned that this area is equal to total electron concentration, and that can be obtained through this integration. And this area indicates the whole concentration, and that can be obtained from this integration. In intrinsic silicon material, the N and P, the number of electrons and holes are identical because they are created together in pairs. The number was n sub I, 10 to the 10 per cubic centimeter for silicon. What about the N-type silicon material this time? Definitely, as we have learned, the number of electrons is governed by dopant concentration, donor's concentration. Okay, and this n sub D is much higher than the whole concentration P. So this equation cannot be valid in N-type silicon material. And on the right hand side, you can clearly see that the area indicating in electron concentration is much wider than the area indicating the whole concentration. Okay, so why is that? Let's go back to the first step. Here is energy band diagram for N-type material. So as we know, the Fermi function, Fermi energy level, in intrinsic silicon material, Fermi function has been placed at mid-gap, middle point of the band gap. But now, the Fermi energy level for N-type silicon material is placed near to the conduction band edge, right? And to have known the carrier distribution, we need two information, one of which is the density of states for N-type silicon material, the other of which is a probability of occupancy, probability of finding an electron in each energy state in N-type silicon material. So we need two info. So density of states, that is kind of, the well set up, well built in chairs, seats in baseball stadium. So even though we have doped the silicon material with the dopant atoms, still the silicon material is, the major one. Crystallinity of silicon materials for N-type silicon material has not been totally, modified at all. Even though very few dopant silicon atoms are replaced with the donors, but that wouldn't affect the crystallinity of silicon material. In other words, a few not allowed people has entered into the baseball stadium that wouldn't affect the total number of people who has officially purchased a ticket. Okay, so in terms of density of states for baseball stadium or for N-type silicon material, the density of state itself might not be modified at all because of the dopant atoms. So here, I'm going to use the identical density of state for pure silicon material. But the thing that was changed is a probability of finding an electron in N-type silicon material. Why this probability of occupancy has been modified? Because the energy level of Fermi energy level is slightly changed. In undoped silicon material, the Fermi energy level is placed in the middle of band gap. But now it is shifted upward near the conduction band edge E sub C, right? So here, the Fermi energy level, the Fermi function value is 1/2, right? So this whole curve, this solid line whole curve is originally, it was, if I'm drawing the Fermi function curve matched to the energy band diagram again here, maybe originally in pure silicon material, it looks like that, okay, 0.5. But now this curve Fermi function has been shifted upward. Because of what? Because of the upward shifted Fermi energy level. Then maybe here, this function will be multiplied with the probability of occupancy in conduction band. And maybe if I zoom in this region, this is original Fermi function, but now the upward shifted Fermi function be like that. Okay, so for given energy state, say here, the probability of finding an electron becomes much higher. Okay, so here the constant times originally in pure silicon material 0.01, but now in n-type material instead of 0.01, that would be 0.1, so 10 times higher. More electrons can be found. Where? At this energy state, maybe here, E1. Okay, so the final curve shape in conduction band would be much bigger. Compare against what? Compare against the original one. Let's go back to the original one here. Take a look at this figure. For pure silicon, undoped silicon, the number of electrons in conduction band should follow this distribution. Now, in n-type material, the curve becomes bigger and bigger. So let's redraw it. So this red colored one indicates N over E of pure silicon. But this black colored one indicates N over E of n-type silicon. Okay, so now you can compare the area below each curve, this area and that area. Okay, so now the area indicates electron concentration. Definitely in n-type silicon material, the n, small n, electron concentration is way higher. For example, in intrinsic case, that is 10 to the 10. Electron concentration is 10 to the 10 per cubic centimeter. However, once the donor has been injected, say 10 to the 16 per cubic centimeter, so this amount of donor has been injected into the pure silicon, then how many electrons do we have in this n-type silicon material? Because all the donors should be fully ionized into the silicon material at room temperature, so the total number of free electrons is 10 to the 16, which is much higher than n sub I, that is 10 to the 10. See here the area difference, okay? N-type versus pure silicon. Okay, then what about the hole, the minority carrier in n-type silicon material? Originally, the hole concentration, this is a P of E of pure silicon material, that is equal to Ni 10 to the 10 per cubic centimeter. and this area, whole area, should be matched to the 10 to the 10, 10 billion. Now, donors has been injected so that the number of free electron has been increased a lot and matched to the donor's concentration. However, following the mass action rule, N times P should be equal to Ni square. So in N-type material, type silicon, the whole concentration, minority carrier concentration, is equal to Ni square over N. So if I'm using this number, 10 to the 16 here, then you're gonna get 10,000 holes available per cubic centimeter. Okay, so minority carrier concentration has become super low. Originally, without any dopant atoms, the silicon material has 10 to the 10 billion holes per cubic centimeter. But now, because the silicon material is doped with donors, the number of electrons is increased a lot up to the donor's concentration. However, the minority carrier concentration has been decreased a lot. Okay. Now let's move on to the next one, p-type material. That is, we're gonna do the similar work that we have done in previous slide. Instead of N-type, we're gonna use a p-type. What happened here? See the result on the right hand side here. The area indicates mole concentration that would be governed by acceptors concentration. Suppose that 10 to the 17 per cubic centimeter. Then what is this area? The area is N is equal to P Ni square. So 10 to the 3,000 electrons available. Okay. And the physics is, in p-type silicon material, its Fermi energy level becomes closer to the valence band edge. So dense of state, no change. Okay. And however, the probability of occupancy shifted downward. Okay. So here the Fermi energy level is well aligned to the energy band diagram on the left hand side here. Line here. And if you do multiplication between density of state times 1 minus f of e, the probability of finding hole, you're gonna get the whole concentration. Okay, so I guess this is the similar work, so you can do that by yourself. The last slide in this lecture note is dependence of Fermi energy level on temperature. So I guess you may look for the contents and topics to be delivered in this lecture slide by yourself. Because what? Because of what? As temperature increases, let's go back to the slide here. Herein. As temperature increases, see here, N is much, much higher than ND. And in the end, at very high temperature regime, see here, N is equal to Ni. Here, notice that N sub I is not anymore 10 to the 10. Whenever I'm saying 10 to the 10, that is the number at room temperature. Now I'm talking about very high temperature. So this number N sub I is way higher than 10 to the 10. Okay, so instead of using number, I have used the symbol N sub I at this high temperature. Okay, so at very high temperature, Ni value is much, much higher than the doping concentration that I have designed. Okay. Then here, previously I mentioned that at very high temperature, the silicon material becomes intrinsic, even though it has tons of donors and acceptors, impurity atoms in it, but it doesn't matter. Temperature matters. So depending on the temperature, the doped silicon material can become intrinsic. Again, depending on the temperature, especially at very high temperature, even though the silicon material is doped with acceptor or donors, it doesn't matter. The doped silicon material becomes intrinsic, becomes pure. Why becomes pure? The meaning of becomes pure means the role of donors and the role of acceptors is meaningless. We have learned the role of the donors and acceptors. What was it? The role of donors is to modify and to govern the total number of free electrons. But now, at this very high temperature, the donor's concentration cannot govern the total electron concentration. Why is that? At this very high temperature, the covalent bonds between two neighboring silicon atoms has been broken a lot. So EHP, electron hole pairs, are created a lot, even higher than the donors and acceptors concentration. So if I'm using the number 10 to the 18, I have doped the silicon material 10 to the 18 at room temperature, but at say 600 Kelvin, the n sub I is 10 to the 21. Then this number 10 to the 18 is nothing compared against the 10 to the 21. The total number of free electron 10 to the 21 is governed by how many electron hole pairs are created at this high temperature. Okay, the total number of electrons at this high temperature, such as 600 Kelvin, is not anymore dependent of doping concentration. Because the donors and acceptors concentration is much lower than the electron hole pairs happened at this high temperature. Okay? So this whole physics can be redrawn in this energy band diagram again. So this is not the real energy band diagram. Just for your information, I have drawn the energy band diagram overlapped with another x-axis, net dopant concentration. Again, notice here that x-axis in the energy band diagram indicates the physical location of your own sample. But herein, I have overwrite the x scale of net dopant concentration in energy band diagram. So if net dopant concentration, simply speaking, Nd minus Na, net doping concentration is say 10 to the 16, then at room temperature, okay? So Nd is higher than N sub A, so that is N sub D. Then using this equation, you can plug in the 10 to the 16 here, and you know this number, and you know the position of conduction band edge, then you can solve this equation for E sub F. Then you're gonna get this point because this y-axis indicates energy. So at this point is matching to the Fermi energy level. Okay, you can repeat this work for different net doping concentration. For example, 10 to the 18. So plug in the 10 to the 18 here. 10 to the 18. You know this number, you know this, and you can calculate the E sub F. So if you do this math work, you're gonna end up the Fermi energy level is now existing at this energy level and draw it here. So repeat this work over all the net dopant concentration, and you're gonna get this data line. Okay. And now let's increase the temperature. Instead of 300 Kelvin, let's use 400 Kelvin here. What would be happened? The data line becomes like that. But intrinsically, you can estimate, intuitively, you can estimate it. If this temperature is 500 Kelvin, 600 Kelvin, whatever the doping concentration is, it is meaningless. Always the Fermi energy level can be found in the middle of band gap because the silicon material is undoped, kind of undoped. It becomes intrinsic. Even though it is doped with many donors and acceptors, but the role of donors and acceptors has been lost. In other words, the silicon material has become intrinsic. It was extrinsic. It was doped. That's true. But at this very high temperature, such as 600 Kelvin, 500 Kelvin, the doped silicon material has become intrinsic, so that the Fermi energy level for the silicon material is located in the middle of the band gap. So if I draw the EF for maybe 700 Kelvin or 1100 Kelvin, even more, then this curve would become asymptotically approaching to this line, just a straight lateral line. Okay, you can intuitively guess. If you have any trouble to understanding this, feel free to asking TA or leave your text message in chatting window, then I will get back to you. Okay, so please read them out, read the summary section by yourself. Okay, that's all for lecture note 6. What is the number of the lecture note? That is 5. Okay, 5. So we're done, and I'm going to give you a 15 minutes break time. It's now 1:44. Let's meet up at 2. Okay, so let me be here to answer your question. If you have any question, leave your question in chatting window, or you can turn on your microphone. We can chat together. So let's meet up at 2.